the last lecture will be given by Rahul Ilango, and we will hear about another exciting result. It's in about arithmetic, assuming some cryptographic assumptions.
All right, so thank you very much for the introduction and coming to my talk. I will do my very best not to keep you guys away from lunch very soon. So this is joint work with Jiaqu Li, who you heard about in the last talk, a fantastic undergrad at Tsinghua, and my advisor, Ryan Williams. And so for the people, I did talk about this earlier in the semester in the meta complexity seminar. That talk I had crossed out the bounded arithmetic part, but for this talk, I've highlighted the bounded arithmetic talk. So, okay. So this talk is going to be about the unprovability of the dual weak pigeonhole principle in certain theories. So what is the dual weak pigeonhole principle? It's something we've heard about already. It just says if you put n pigeons into 2n pigeonhole, then there must be a lonely pigeonhole. No, a pigeonhole without a pigeon. And the factor 2 here isn't so important. You want some gap, but the factor, well, let's just deal with the case where there's a factor of 2. And so like this simple result is very nice for us complexity theorists because it implies various things. So like, for example, the fact that there is a Boolean function on n inputs with high circuit complexity follows, for example, from this dual weak pigeonhole principle. Okay, and so the formalization that we're going to deal with in this talk, and I'll be a little bit informal here, I'll be more formal later, is some sort of for all exists for all statement. We're saying that, let's say, for all circuits that map n bits to n plus 1 bits. So this is, there are 2 to the n inputs here. There are 2 to the n plus 1 inputs here. So this is this factor 2 that we saw before. There exists some string of length n plus 1 that is not in the range of the circuit. So for all x, c of x is not equal to y. So this is a for all exists for all statement. Might not be clear yet why this is important, but this will come up again later. Okay, so we have some nice combinatorial principle. We can ask how hard is it to prove in various theories. And so thankfully we've heard a lot about bounded arithmetic today. And so we've heard about PV1, which for my talk, I mean, thankfully we've already seen like a nice definition of it, but for my talk, all you need to know is that this is some proof system corresponding to polynomial time reasoning. You also need to know a witnessing theorem that I'll tell you about later, but for now, just some nice proof system corresponding to polynomial time reasoning. In fact, just to give you some intuition, all I am going to say about PV1, I just want to give this example. On the one hand, PV1 is kind of weak in that it can't prove that any one-way permutation is surjective. But on the other hand, it's really strong in that it can prove the PCP theorem. So it can't prove like these very basic facts about groups. And on the other hand, it can prove the PCP theorem. So this is, in some sense, it's very powerful. In some other senses, it's a condition. Oh, no, but it can't prove any one-way permutation. The condition is in the statement. Yeah. It's very sneaky. Okay, so we have PV1. And so now let me tell you what our main result is. So our main result is PV1, under some assumptions, cannot prove the dual weak pigeonhole principle for PV functions, which if you know about bounded arithmetic, this is a precise formalization. I'm not gonna go through it in detail. So, but PV1 cannot prove the dual weak pigeonhole principles under the following assumptions. So the first assumption is that NP is not in co-AM infinitely often. So under a de-randomization assumption, this is basically just NP not equal to co-NP infinitely often. So that's a nice complexity theoretic assumption. The second assumption might be less familiar to the audience, but we'll also hear about it later in the day. Sub-exponentially secure, whatever that means, indistinguishability obfuscators, whatever that means. I'll tell you about them later in the talk. So assuming that these two things exist, you can prove that PV1 does not prove the dual weak pigeonhole principle. And as a corollary, or pretty much directly, you get that APC1, whatever that is, Igor defined it in his last talk, if you're, is a strict extension of PV1. And why this might be a little bit, why this is interesting is like, so as Igor mentioned in his talk, this class kind of informally corresponds to probabilistic polynomial time reasoning. This class kind of informally corresponds to polynomial time reasoning. So you might think, you know, P equals VPP, so then maybe these two things are the same. But in fact, they're under these assumptions, they're different. And I should say, or okay, maybe I'll say this and then take questions. So there has been some prior work on this, so that you can get an oracle separation of APC1 versus PV1. This was shown by Jahrbeek, and you can also get that the dual-weak pigeonhole principle is not proved in PV1 under the assumption that P is in size n to the k, but maybe that's a unlikely assumption, I guess, depending on what you believe. Okay, any questions about this?
Assume both of these conditions.
Yeah, assume both of these conditions. Yeah, sorry.
So this unprovability is based on both. But and then you say that Jahrbeek already proved that APC1 is not conservative over PV1.
Or I said he gives an oracle relative to which. Like
oh, it's not from this one.
Right, like yeah, there's an oracle relative to which you can't prove this, and this was like saying maybe under reasonable assumptions that in our world you can also not prove this. Right.
Previous result assumed circuit lower bounds.
The previous result, you're saying that
Under circuit
criteria
lower bounds.
under circuit upper bounds.
Oh, upper bounds.
Yeah, this is an unlikely, well, I guess it depends who you ask, but maybe this is an unlikely assumption. Right, good. Okay, cool. So let me tell you a little bit about how this is proved. So the proof overview actually breaks down into two very nice steps. So the first step is to say, for contradiction, suppose PV1 did prove the dual-weak pigeonhole principle. Okay, what do we get at this? And so there's a very nice hammer we can use. So by the KPT witnessing theorem, which I'll tell you about in a bit, but it's just a nice hammer, tells you that there's some sort of algorithm for a related problem, which I'll also tell you about later, called circuit range avoidance. So you transition from a provability in PV1 to an algorithm for some related problem. Okay, and I'll tell you about that later. And then the next step is to show that actually this algorithm doesn't exist. And this is the part that uses indistinguishability obfuscation. So this part is, oh, sorry, not that. So assuming you have indistinguishability obfuscation, this gives you a non-deterministic algorithm for verifying unsatisfiability, or in particular, NP is in co-AM infinitely often. Okay. So what I'm going to do in the rest first part of the talk is I'm going to tell you how to do this. So this is a relatively standard thing, but I just want to go through it. And then in the second part of the talk, I'll tell you about this. Okay. So I mentioned this problem, circuit range avoidance. So what exactly is this problem? So I don't have time in my talk to talk about all the literature on circuit range avoidance. It's a very nice problem with lots of interesting results, but let me tell you a little bit about what's known about it and what is going to be relevant for our talk. So it's this problem that was defined by Kleinberg, Korten, Metropolsky, and Papadimitriou. They were interested in total function problems in the polynomial hierarchy. And as you can maybe tell from this input-output description, it's very closely related to the dual-weak pigeonhole principle. You're given some circuit that maps n bits to m bits, where m is greater than n, and your goal is to output something that's not in the range of the circuit. And there are many such strings just by a counting argument. And, so as a result, there's a very simple randomized algorithm. In fact, the randomized algorithm is so simple, it doesn't even look at its input. It just outputs a random string. Okay, and so you have a randomized algorithm, and an extremely natural question to ask is, does there exist a deterministic algorithm for this problem? So what do you guys think? Who thinks that there should be a deterministic algorithm? Who thinks there should not be a deterministic algorithm? Yeah, so I've sort of given you the punchline away already, but yeah, under the same assumptions that I talked about earlier, there's not a deterministic algorithm. And what makes this kind of interesting is that it was unknown prior to this whether there's any plausible assumptions under which you can show that avoid does not have a deterministic algorithm. It wasn't even clear what the ground truth was. What was known was that if you did have a deterministic algorithm, you had all sorts of amazing explicit construction consequences. You get explicit truth tables with high circuit complexity, you get good explicit Ramsey graphs, true source extractors, rigid matrices, and so on. And these were consequences that were really nice and things we didn't know how to prove, but they were all things that we believed. So it wasn't like evidence that a deterministic algorithm shouldn't exist. It was just nice consequences of it. Okay, so that's what I wanted to say about range avoidance. Now I'm going to come back to how, if you proved in PV1 that you prove the dual-weak pigeonhole principle in PV1, how that implies some sort of algorithm for range avoidance. Is there any questions about range avoidance before I move on? Okay, great. So there's this hammer I mentioned, which is KPT witnessing, which is proved by Krychek, Pudlak, and Takuti in 91. And it basically says, I'm going to state it informally and then just tell you what the consequences for our problem is. If PV1 proves some sort of for all exists for all statement, then there is some sort of algorithm witnessing this. And I'll be more specific about what I mean by algorithm witnessing it in a second. But in our setting, you have the dual-weak pigeonhole principle, which was this for all exists for all statement. And so as a result, kind of directly, a direct consequence of KPT is that if PV1 proved the dual-weak pigeonhole principle, there is, and this is where the algorithm was put in quotes, a constant round polynomial time deterministic student-teacher algorithm for avoid. I'm going to tell you what that is on the next slide. I'll walk you through it. But it's some sort of algorithmic way to solve avoid. So what exactly is the algorithm? So the algorithm looks like this. So on the one hand, you have a very wise, helpful teacher like Rahul. And on the other hand, you have a misguided but well-meaning kind of dinky student. On the other hand, like Rahul, and the goal is the student wants to solve a void on some circuit. And so what does the student do? The student, looks at the circuit, is like maybe isn't so diligent, and oh, sorry. So what is a student? A student, as we all know, is k deterministic polynomial time algorithms. And so just A1 up to AK. And so the student will look at the circuit and say, hey, I think that Y1 is not in the range of the circuit. And then the very wise teacher will look and be like, well, okay, that was a good try, but actually it is in the range of the circuit. And it hands back some X1, which is in the range. The student goes back, oh, okay, very good, very good. Oh, yes, I know. Oh, Y2, I think Y2 is not in the range of the circuit. And the teacher's like, okay, you're getting a little bit better, but gives back an example. And importantly, the student is allowed to see the counterexample. And so basically a K-round student-teacher game is a game like this where the student will eventually find a counterexample in at most K-rounds. And the KPT witnessing theorem will show that you had an algorithm that succeeds in a constant number of rounds. Is the definition of this clear? Oh, and I want to mention that it's really important that for our purpose, that these algorithms are deterministic, because as I mentioned earlier, if you allowed randomness, there's this very simple algorithm for the student where he just says like uniformly random. Okay, awesome. So returning to our proof overview, we've done the first step. They said, if PV1 proves the dual-weak pigeonhole principle, then by KPT witnessing, there's a student-teacher algorithm for circuit range avoidance. Oh, yes.
The number K depends on the length of the proof or the...
Well, that's a good question. Actually, I don't know. I mean, so it's going to be a constant. I don't know what the dependence on K is. Depends on the proof. Depends on the proof. Yeah. Does it depend on the, okay, yeah.
Induction or something.
Okay. So it's some constant. It'll depend on the proof. And so this is the first part. And now the second part that I want to tell you about is that if you assume the existence of sufficiently good indistinguishability obfuscation, which I still haven't told you what it is, then that implies that NP is in coam infinitely. Okay, so let me tell you a bit about indistinguishability obfuscation. So the study of cryptographic obfuscation, at least the modern study of it, dates back to this paper by Barak et al. In 2001. And the goal, I mean, intuitively, the goal of obfuscation is you're handed a circuit C, and somehow you want to scramble this circuit into some obfuscated circuit C that computes the same function. But ideally, and I'm going to be a bit informal here, I'll see why in a second, like this circuit doesn't really tell you anything. And so one way you can formalize it is that anything you can compute using the obfuscation, you could compute with black box access to the function computed by this. I'm going to be a bit hand wavy here, but this is kind of saying all you can do with the circuit is run it. Like you won't be able to learn any other information based on, except when you ran it on the input, you saw what the output is, so on. And this would be a really great, really strong notion, except that it doesn't exist. So there's a nice proof. It's almost halting-esque, where you take an obfuscation, you run it on itself, you do something, and then you get a contradiction. So this definition is too strong. And so, what did the cryptographers do? I mean, they're very brave. This didn't deter them. If it's impossible, let's do it. And they came up with a different definition, which is indistinguishability obfuscation. So this is the definition we're going to be talking about. And it says, what is an indistinguishability obfuscator? It's some sort of randomized algorithm. It takes as input a circuit. It also takes as input a security parameter, but let's not worry about that. For now, I'm going to omit writing it. And it has the following two properties. The first property, as you'd expect, is that for all circuits C, the obfuscator will output a circuit computing the same function. And there's actually one thing I want to stress about this. If you were making this definition, you might not have to aim for perfect functionality. I mean, maybe with extremely small probability, you'll output a circuit which computes a different function. But it turns out it turns out you can actually hope for this stronger guarantee. Perfect functionality, we're going to use it. This is going to be important. Okay. So perfect functionality, remember that, that'll come back later. And so the security guarantee, and this is the meat of the definition, is something that's much weaker than what was on the previous slide. It says whenever you had two circuits of approximately the same size computing the exact same function, then when you obfuscate the two circuits, so you have the IO of C and the IO of C prime, they're approximately the same size, they compute the same function, you can't tell which circuit you started. So like after you've obfuscated this, no adversary circuit of size C with a lambda to that epsilon is able to tell the difference between whether you obfuscated the first circuit or the second circuit, except with extremely small probabilities. So let me give you some intuition for this. Let me say, like, well, here's an example of a trivial indistinguishability obfuscator. It's not an efficient one, but it's trivial. You just take your circuit and find the lexicographically first circuit that computes the same function. So this thing will, that indistinguishability obfuscator takes a lot of time, but it will guarantee this. So whenever you have two circuits that compute the same function, it's going to give the same output. But that's under an unlikely assumption. One of the crown jewels, I mean, you heard about the Joule theorem in proof complexity. One of the crown jewels of cryptography in the past few years is that actually you can construct sub-exponentially secure indistinguishable obfuscation under well-founded assumptions. So this is this paper of Jane Lin and Sahai. If you're curious, these assumptions are sub-exponentially secure. Learning parity with noise is sub-exponentially secure. Some bilinear map is also sub-exponentially secure, and then there are NC0 PRGs with arbitrary polynomial edge. Anyway, okay. They're very nice assumptions, and under those assumptions you actually get sub-exponentially secure IO. Sorry, you have a question? Oh, no.
I do.
Oh, okay.
How is epsilon quantified?
How is epsilon quantified? Okay, so there will exist some epsilon. This is just some fixed constant. Maybe think of it as 1/100 or something like that. Okay, good. So now, what do we need to prove? What we're going to show, or actually not what we're going to show, but what we show in the paper is sub-exponentially secure IO exists, and there was a student-teacher algorithm for void, as I described on the previous slide, then NP is going to be in co-AM infinitely often. And in this talk, I'm not going to show that. I'm going to tell you a little bit about a simpler proof, which is we'll still assume sub-exponentially secure IO, but instead of assuming there was a constant number of rounds, let's just assume there was one round, which is just that a void has a deterministic algorithm. So let's simplify things. There's not a constant number of rounds. There's one round, which just means you can solve a void in deterministic polynomial time. And actually, then you can get a stronger consequence, which is NP is equal to co-NP.
By the way, this is a void FP, but you've been talking about avoiding a circuit, computable function.
Right. Yeah. So the translation is that you have like this eval function. You take like this eval output, right? And then, does that answer your question or no?
So the question is whether it makes a difference.
Oh, okay. It doesn't make a difference. Okay. Right. And just to unpack what this means, because we want to give a non-deterministic polynomial time algorithm that checks if a formula is satisfiable. Oh, sorry, it's unsatisfiable. Okay, and so how much time do I have? I have 5 minutes, I guess?
5 minutes.
Yes, okay. So what does the reduction look like? So we're given some formula phi on n inputs. What's our non-deterministic algorithm? The algorithm is going to say output unsatisfiable. If there exists, it's going to existentially guess a y of length n+1 and some r. So these are just two strings. It's just going to guess two strings. We'll worry about what they are and what their meaning is later. It's going to guess two strings, and it's going to check the following condition. So what is this condition? So I'm going to use notation. I'm going to say I'm going to let avoid stand for its deterministic algorithm. I'm going to let IO stand for its algorithm. So what I'm going to say is you have to output onset if you can guess a y and an r, such that when you run the avoid algorithm on the obfuscation of some circuit. I actually haven't told you what the circuit is yet. We'll come back to it. It's some circuit that you can construct given phi and y. Come back to it later. With randomness r, you get back y. Okay, so this is the reduction. Let me recap it again. You're just going to run the avoid algorithm on an obfuscation of some circuit with randomness r, and you're going to guess the y to put here, and you're going to guess the r to put here. And you're going to see if you can get back y. Now I haven't told you what this circuit is, but hopefully you agree with me that as long as that circuit is efficiently constructible, this is a non-deterministic polynomial time algorithm. Does that make sense? Yes. Okay, so let me tell you what the circuit is. Oh, and I should mention also there's the security parameter, which I've been hiding, but it's some polynomial in phi. Let's not worry about it. So what is this circuit? This circuit, if you're familiar with the cryptographic literature, it's basically this construction of witness encryption from IO. The circuit in phi, constructed from phi and y, is computing the following function. Given x, it'll output all zeros if phi is not satisfied at x. On the other hand, if phi is satisfied at x, it's going to output y. So it's something that if phi happened to be unsatisfiable, this is just the all zeros function. On the other hand, if phi is satisfiable, then y is going to be hidden somewhere there. And just some remarks. So this is exactly a circuit that we can use range avoidance on because it's mapping n bits to n+1 bits. And also something that's kind of interesting about this circuit, it actually has range of exactly 2. Yeah, I mean, this thing has a very small range. Turns out it's already hard to solve range avoidance on this. And so, okay, I guess I have 3 minutes. So, right, let me see if there's any questions in this slide first. I can tell you a bit about soundness. The proof of soundness isn't too hard to see. But if there's any questions.
Confused. avoid, you're assuming it's deterministic, and that's why this is NP. But if you take the trivial randomized algorithm, then it's MA.
Right. So what'll happen is so you're saying why not? What happens when we plug the randomized algorithm into here? That's what you're asking. What happens?
Go ahead.
Is that what you're asking, or are you asking?
Yeah, I'm asking exactly this.
Okay. And what'll happen is then this argument won't work. This is not going to be a witness of unsatisfiability. In fact, for every phi, there's going to exist an R and a Y such that this is true.
Also, the randomized algorithm, you can't control that Y.
Yeah, it's just it's just going to.
You can't guess what the randomized algorithm is going to do. It's going to pick a uniform random tree.
But in this case, it'll still. Okay. Yeah.
Thank you.
So if you replace the randomized algorithm here, it's going to say everything's unsatisfiable. So it's going to be. Okay, so let's just go over the proof of soundness because that's relatively short. Just as a reminder, here's the reduction. Suppose, and we basically already said this, if the reduction says phi is unsatisfiable, then what does that mean? It means that there existed a Y and an R such that this condition held. Okay. By the correctness of the avoid algorithm, here's crucially where the fact that you're using it's deterministic and doesn't make errors. Is that Y is not in the range of this obfuscated circuit. If avoid was a randomized algorithm, you don't necessarily know this is true. And now, by the perfect functionality of IO, here's where you're using that it has perfect functionality. You know that Y is not in the range of C phi Y. And then by the definition of C phi Y, this means that phi is unsatisfiable. Okay, did that make sense? Okay. So the harder direction is completeness, which I won't tell you about now, but if you're interested, you can come talk to me. The proof isn't too long. But thank you very much for listening, and if you have any questions, I'll be very happy to answer them.
So the reason you get AM is because IO has a failure probability?
Yeah, the reason why you get AM actually is you don't get it in this one round case, but when you go to a student teacher algorithm with constantly many rounds, it turns out you need to do some approximate counting. It probably won't be clear from this, but from this sketch. But when you go to constantly many rounds, it turns out you need to do some approximate counting. That's why you get it. Yeah.
Can you rule out avoid an FCPP to say?
Yeah, I think so. If avoid was an FCPP, then under a de-randomization assumption, it's an FP. Oh, right. Yeah. So Yuval had this nice question. So one of the reasons why you might be interested in studying the complexity of avoid. Why would you be interested in this thing actually having a deterministic time algorithm? It's because this gives a complexity theoretic way of actually constructing all of these objects we think should have explicit constructions. It's like a central thing, such that if you have a deterministic algorithm for this, you construct all the things. If you have an NP oracle, you still get it, as you should, but if you want to just get some condition under which you can deterministically reconstruct Ramsey graphs, two-source extractors, whatever, is there some other problem or some other assumption under which you can get that? Does that make sense? And so you can get a list construction under classic de-randomization assumptions. You can construct a list of objects such that one of them is going to be a good two-source extractor. But what if you want to know exactly? You want to have one object, you say this is two-source extractor, and in some sense, we already have it. You take the digits of pi, that'll be your two-source extractor, or whatever. Yeah, it'll work. But can we give a complexity theoretic? Oh, did that answer your question? Okay.
Yeah, so what happens if the circuit is an AC0?
Yeah, great question. So it turns out this approach under reasonable cryptographic or plausible cryptographic assumptions will rule out even AC0 or even NC0 for NC0 where every output bit depends on those 4 input bits. Okay, it depends what cryptographic assumptions you believe. NC03 is an open question. There's been some work recently that came out recently that gets it in a large stretch regime, and NC02 we know that exists in polynomial time. Yeah.
For those applications, you only need to solve avoid for uniform algorithm.
Yeah.
And
right.
Your approach only rule out.
Only rule out. Right, but can you, so can you come up with a nice assumption? I mean, if you generate strings with large poly complexity, right, you'll have this, but, can you, that's something nice, yeah. Oh, yes.
So what's your opinion about the statement that avoid is in like average p on any central distribution?
Remind me, average p means you can make error in two directions and understand.
Yeah, let's say you can make errors.
Yeah, but yeah, I would say yes, and I would say just take the digits of pi.
That's true in random oracle, right?
Huh?
That's true in random oracle.
Oh, that's true. I see.
Actually, in our paper, we have to, like, for complexity, like, you can solve it if on average. Hey.
Choose.